Hi everyone. In this video we're going to talk about spanning sets and minimal spanning sets. So let's just recall that the span of a set of vectors is the set of all linear combinations of those vectors. And we write that the span of whatever set of vectors we have is equal to the collection of possible linear combinations of all those vectors. And we say a set of vectors spans a space if that collection has as its span the entire space that we're interested in. In particular, at times we're interested in whether or not a set of vectors spans the entire space that we're working in. So set S of vectors v1 through vn spans R sub m if every vector in R sub m can be written as a linear combination of vectors in the set S. And finally, another topic that we want to talk about in the context of the examples we're going to do in a minute is this idea of a minimal spanning set. So here is our last definition that we need to make. A set S is a minimal spanning set for the space W if first, if it's a spanning set, it needs to span all of W, and that means that every vector in W can be written as a linear combination of vectors from S. So S has to span W, and moreover, it's minimal in the sense that no proper subset of S will also span W. Now there's a lot of ideas here, but it all can be decrypted for any set of vectors by just looking at the row equivalent reduced echelon form, or even just echelon form, of the matrix of vectors in the set S. So let's look at a couple of examples and answer some questions related to these three things. So these are the two questions I want to address in the next couple of examples. And the first one says that if we're given a set of m-dimensional vectors, do they span Rm? In other words, are you able to write down every vector in m-dimensional space as a linear combination of those n vectors? Given that S does span the space, we can ask, is it minimal? And the answer to both of these questions can come from just looking at the row equivalent echelon form of the matrix that you get when you stack up those vectors as the columns. So let's see how that works in practice. Okay, so here we have a set of 4 vectors in 3-dimensional space, and I'm going to call these v1, v2, v3, and v4, and ask these questions about this particular set of vectors S. So first we can ask, we're given this S, and we want to ask if it spans Rm. In this case, we're talking about 3-dimensional vectors, so we ask if it spans R3, all of 3-dimensional space. To answer that first question, we need to figure out whether or not we can write every vector in R3 as a linear combination of these 4 vectors. So we can set up the following matrix equation. And if you think about multiplying this out, as we've done a couple of times already now, the matrix product of these two matrices on the left-hand side is going to give us exactly what a linear combination of those 4 vectors would look like, A1 being the coefficient of V1, A2 being the coefficient of V2, and so on. This x1, x2, x3 on the right-hand side is intended to represent an arbitrary vector in Rn, and the existence of a solution to this case where x1, x2, x3 can be anything is going to tell us whether or not the answer to question 1 is yes or no, right? So if we can always find a solution that will produce the coefficients for a linear combination, then we know that the answer to the question is yes. So if I start doing my row reduction algorithm, and I'll spare you the details, that's my row reduced echelon form of the matrix of vectors up here. This matrix has a pivot in every single row. So that means it's not possible to get a row of all zeros, which would be the only scenario in which we would have no solution to our original equation. So this thing always has, in fact, infinitely many solutions because there's a free variable. So we know that the answer to the question, does S span R3, is yes. So to answer the second question, is this a minimal spanning set, we can also look to the echelon form of the matrix. This tells me that A3 is free. So that means I could set it to be anything I want, and I'll get coefficients A1, A2, and A4 that will satisfy the equation. So if we pick A3 to be 0 in the general solution, we'll get an expression for our x vector in terms of just vectors 1, 2, and 4. And since we'll be able to do that with every different vector x, we know that we don't actually need any contribution from V3 to write these things down. So in fact, this set S is not a minimal spanning set. However, making this analysis allows us to identify a minimal spanning set. Right? This says that all we need to span the space are V1, V2, and V4. So if we have those, we'll have enough vectors to span the space. And we don't even need to recheck to see if it's a minimal spanning set, because we can just go back to look at the work that we've already done. So let's just think about deleting V3 from our whole analysis, right? So that would mean that we would be deleting this. A3 wouldn't be here anymore. So when we go through to compute our row echelon form, this wouldn't be here. And what we have left is a 3x3 matrix that has a pivot in every column and a pivot in every row. And considering this idea that we wrote down before, that if there's a pivot in every row, this matrix will always have a solution, we can see that that's still true, and this still does span, this smaller set still spans the whole space. So just in conclusion, let's write down a couple of observations and facts. First, a set of vectors spans all of Rm if that matrix that you construct has no 0 rows. Second, the set is minimal spanning if every column has a pivot, because a column corresponding to a free variable is an indication that the vector that corresponds to it is extraneous. So not only does the echelon form tell us whether or not it's a minimal spanning set, if it's not, it finds one for it. So the set of vectors which correspond to the columns that have pivots form a minimal spanning set. Okay, let's stop here for now. In the next section, we're going to work more with minimal spanning sets and talk about dimension and bases of a vector space.